Section: Introduction. In this section, we explore the background and preliminary studies related to token efficiency in chain of thought (COT) sequences and how it affects the reasoning performance of large language models (LLMs). We begin by addressing a key question regarding COT efficiency. Does every token in the COT output contribute equally to deriving the answer? Essentially, we want to determine if there are redundant tokens in COT sequences that could be removed to enhance efficiency. Token redundancy is a well-known issue in LLM efficiency and has recently gained attention in the context of prompt compression, which aims to eliminate unnecessary tokens from input prompts to save on API token usage. To tackle this, selective context measures the importance of tokens based on the semantic confidence of LLMs. This method can be applied to COT tokens generated by LLMs. However, we note that there are limitations to this approach. For instance, tokens at the end of sentences often receive lower importance scores due to the nature of LLM perplexity, which can skew the measurement of their factual importance. Additionally, the unidirectional attention mechanism in causal LLMs may miss critical information needed for assessing token importance. To overcome these challenges, LLM-LINGUA2 suggests using a bidirectional model, like BERT, to measure token importance more effectively. In our study, we adopt LLM-LINGUA2's method to evaluate token importance in LLM COT outputs. We find that, similar to regular text, the semantic importance of tokens in COT outputs varies significantly. For example, mathematical equations typically play a larger role in reaching the final answer, while semantic connectors like so and since contribute less. These insights reveal the presence of token redundancy in LLM COT outputs and highlight the potential for improving COT efficiency by removing these redundant tokens. Section Summary. In this section, we investigate the varying contributions of tokens in chain of thought (COT) outputs to enhance efficiency by identifying and eliminating redundant tokens. Our analysis reveals that certain tokens, particularly mathematical equations, are more critical for reasoning, suggesting that we can improve COT efficiency by selectively pruning less important tokens. Section: COT Recovery. In this section, we explore the question: can large language models, LLMs, restore the chain of thought (COT) process from compressed outputs? Our findings confirm that they can. As illustrated in our figures and detailed in the appendix, examples restored from compressed COTs using LLAMA 3.1 to 8b instruct show that LLMs effectively understand the semantic information in compressed COTs and can restore the COT process. This ability helps maintain the interpretability of compressed COTs. Moreover, when users need it, we can recover and present the complete COT process. In summary, our analysis highlights the potential of removing redundant tokens to improve COT efficiency and demonstrates ILM's ability to restore COTs from compressed outputs. However, allowing LLMs to independently skip unnecessary COT tokens and find shortcuts between essential reasoning tokens is a significant challenge. To our knowledge, this work is the first to investigate COT compression through token skipping. In the following sections, we will detail our proposed methodology. We introduce TokenSkip, a straightforward yet effective method that allows LLMs to skip less important tokens, enabling controllable COT compression with adjustable ratios. This section outlines our methodology, including token pruning, training, and inference. The main idea behind TokenSkip is that each reasoning token plays a different role in reaching the answer. To improve COT efficiency, we suggest trimming redundant tokens from LLM COT outputs and fine-tuning LLMs using these trimmed COT paths. The token pruning process is based on the importance of each token, which we will explain in detail. Specifically, for a target LLM and one of its COT paths, we first assess the semantic importance of each COT token. We then rank the tokens based on their importance. For training, we start with a dataset containing several samples and generate COT paths with our target LLM. We filter out paths with incorrect answers to ensure high-quality training data. For the remaining COT paths, we prune each one using a randomly chosen compression ratio. Each training sample is formatted to include the question, the compressed COT, and the answer. We fine-tune the target LLM to perform chain-of-thought reasoning in a compressed manner while keeping the answers unchanged. To maintain the reasoning capabilities of the LLMs, we also include some original COT paths in the training data. During inference, TokenSkip uses autoregressive decoding. Unlike original COT outputs that may have redundancies, TokenSkip allows LLMs to skip unimportant tokens during the reasoning process, improving efficiency. The input prompt for TokenSkip follows the same format used in fine-tuning. The LLM then predicts the output sequence, which includes the COT tokens and the answer. We illustrate the training and inference process of TokenSkip in our figures. Section Summary. In this section, we demonstrate that large language models, LLMs, can effectively restore the chain of thought, COT, process from compressed outputs, maintaining interpretability while enhancing efficiency by trimming redundant tokens. We introduce our TokenSkip methodology, which allows LLMs to skip less important tokens during reasoning, and detail the processes of token pruning, training, and inference to achieve controllable COT compression. Section: Experiments. In this section, we evaluate our method using the LLAMA 3.1 to 8b instruct and 0.5 instruct series, focusing on two popular reasoning benchmarks, GSM-8K and math. For training, we utilize the training sets from both datasets. Due to computational costs, we assess our method on a subset of the math dataset, called Math 500, which consists of 500 representative problems. We find that the results from this subset are comparable to those from the full dataset. For implementation, we use LLMLINGUA2 to measure token importance and create our compressed chain of thought, COT, training data. The compression ratio is randomly chosen from a set of values between 0.5 and 1.0 for each training sample. We apply LoRa, a well-established method for fine-tuning large language models, with a rank of 8 and a scaling parameter of 16. Our training is efficient, taking about 2 hours for the 7B model and 2.5 hours for the 14B model on NVIDIA 3090 GPUs. During inference, we set the maximum number of tokens to 512 for GSM-8K and 1024 for math. All experiments are conducted using PyTorch 2.1.0 on two NVIDIA GeForce RTX 3090 GPUs and an Intel Xeon CPU with 32 cores. Additional implementation details can be found in the appendix. In our main experiments, we compare TokenSkip to two common length control methods. 1. Prompt-based reduction, where we instruct the model to reduce a specific percentage of output tokens by adding a prompt to the input, and 2. Truncation, which simply limits the number of output tokens. We refer to these methods as prompt and truncation in our results. We evaluate TokenSkip using three key metrics: accuracy, the number of COT tokens, and inference latency per sample. We assess model performance with scripts from DeepSeek Math and use greedy decoding for output generation. Inference latency is measured on a single NVIDIA 3090 GPU with a batch size of 1. We also report the actual compression ratio of the COTs to see if it matches our target. Our main results show that TokenSkip performs well on GSM-8K with the 0.5 instruct series. As the model size increases, we observe less performance loss at higher compression ratios, indicating that larger models are better at finding shortcuts in reasoning. Notably, the 0.5 to 14B instruct model shows almost no performance drop with 40% token trimming, and even at a compression ratio of 0.5, it only experiences a 2% performance decline. These findings demonstrate TokenSkip's potential to reduce COT token usage and speed up reasoning in large models. We also compare TokenSkip with the two-length control methods. The results reveal that prompt-based reduction does not meet the specified compression ratio, exceeding 0.89 even when targeting 0.5. While truncation meets the target ratio, it significantly harms reasoning performance, causing a 79% accuracy drop on GSM-8K and a 21% drop on Math -500. In contrast, TokenSkip adheres to the specified compression ratio while maintaining strong reasoning capabilities, achieving an actual compression ratio of 0.53 on GSM 8K with only a 10% performance drop, resulting in a 1.8 times speedup in average latency. On the Math 500 dataset, TokenSkip reduces COT token usage by 30% with less than a 4% performance decline. These results confirm the effectiveness of TokenSkip. Section Summary. In this section, we evaluate our method, TokenSkip, using LLAMA 3.1 models on the GSM 8K and Math 500 datasets, demonstrating its ability to maintain strong reasoning performance while achieving significant token compression. Our results show that TokenSkip outperforms traditional length control methods, achieving a compression ratio of 0.53 on GSM 8K with only a 10% performance drop, and effectively reducing token usage by 30% on Math 500 with minimal impact on accuracy. Section: Compression Ratio. In this section, we examine compression ratios, particularly those above 0.5. To explore how TokenSkip performs at lower ratios, we created an additional version called More Ratio, which includes compression ratios of 0.3 and 0.4. Our findings, illustrated in a figure, show that model performance declines significantly at these lower ratios. We believe this drop is due to the excessive removal of reasoning tokens, which likely leads to the loss of important information, making it harder for large language models, LLMs, to learn effective chain of thought, COT, compression. Moreover, we notice that More Ratio does not perform as well as TokenSkip with its default settings, reinforcing our hypothesis. Next, we present a comparison of TokenSkip's performance using different token importance metrics. Alongside previously discussed metrics, we include GPT-4o as a strong benchmark. For a given COT trajectory, we prompt GPT-4o to remove unnecessary tokens based on a set compression ratio, without adding new tokens. We also ask GPT-4o to recommend the best compression format for the COT trajectory, which we refer to as GPT-4o optimal. We use all training data generated by GPT-4o to train a version of TokenSkip. By prompting the model with the optimal token, we obtain results for GPT-4o optimal. Our results show that TokenSkip using LLMLINGUA2 outperforms the version with selective context, consistent with our earlier findings. Additionally, using GPT-4o for measuring token importance improves compression performance, suggesting that a more effective COT compressor could enhance TokenSkip further. However, the costs associated with using GPT-4o make it impractical for large datasets. In contrast, LLMLINGUA2, which includes a BERT-sized model, provides a more cost-effective and efficient option for training TokenSkip. Furthermore, GPT-4o Optimal strikes a better balance between reasoning accuracy and COT token reduction, highlighting the potential of flexible compression ratios in COT generation, which we aim to explore in future research. We also adjust the maximum length budget to a specific value when evaluating TokenSkip on Math 500 to ensure a fair comparison of compression ratios. However, this strict length truncation affects the reasoning performance of LLMs, as they cannot complete the full generation. We investigate whether LLMs can reason more effectively using a compressed COT format. Specifically, we assess TokenSkip under the same length budget as the original LLM, for example, 1024 for Math 500. Our experimental results show a significant performance boost for TokenSkip under this length budget compared to those adjusted by compression ratios. Notably, with compression ratios of 0.7, 0.8, and 0.9, TokenSkip outperforms the original LLM, achieving an absolute performance increase of 1.3 to 2.6 points. These results demonstrate TokenSkip's potential to enhance LLM reasoning capabilities within the same length budget. In our case study, we present examples of TokenSkip from the test sets of GSM 8K and Math 500. These examples clearly show that TokenSkip enables LLMs to learn shortcuts between essential reasoning tokens instead of creating shorter COTs from scratch. For instance, in one example, TokenSkip helps LLAMA 3.1 to 8b instruct skip over minor semantic connectors and less significant expressions, while prioritizing numeric values and mathematical equations. This aligns with recent research suggesting that mathematical expressions may play a more crucial role in reasoning than COT in natural language. Additionally, we find that TokenSkip does not reduce the number of reasoning steps but rather eliminates redundant tokens within those steps. Lastly, while chain of thought, COT, improves task performance by mimicking human reasoning, it also adds significant computational demands. Researchers have been looking for ways to reduce this overhead while keeping the advantages of COT. One approach is to simplify, skip, or generate reasoning steps in parallel to enhance efficiency. Another method involves compressing reasoning steps into continuous representations, allowing LLMs to reason without generating discrete word tokens. To limit the generation of unnecessary natural language that has little impact on reasoning, we implement structured syntax and symbols, guiding token usage through dynamic budget estimation. We also prompt larger LLMs, like GPT-4, to compress COT directly and then fine-tune them to reason using these compressed COTs. In contrast, our work focuses on pruning COT tokens based on their semantic importance, using a smaller language model for token pruning, which significantly cuts down on computational costs. Section Summary. In this section, we investigate the performance of TokenSkip at various compression ratios, finding that lower ratios, 0.3 and 0.4, degrade model adherence due to excessive trimming of reasoning tokens. We also demonstrate that TokenSkip, particularly when using LLMLINGUA2 for token importance measurement, significantly enhances reasoning capabilities within a fixed-length budget, while maintaining efficiency by focusing on the semantic importance of tokens. Section: Prompt Compression. In this section, we discuss how the advancements in large language models, LLMs, have increased the need for handling complex instructions and lengthy prompts, which in turn creates significant computational and memory challenges. To tackle this issue, we have looked into various prompt compression techniques. One straightforward method is to use a smaller language model to create shorter, yet similar prompts. However, since natural language often includes unnecessary details, some researchers have opted for implicit continuous tokens to represent task prompts and longer inputs. Other strategies aim to compress prompts by filtering out less informative tokens. For example, selective context evaluates the importance of tokens using the perplexity of LLMs, removing those that are less significant. Additionally, LLMLINGUA2 employs a small bidirectional language model to assess token importance, training it with data from GPT-4 compression to establish a metric for token significance in our work.